Okay, so we'll start the last lecture of this module. You'll have your exam opens today at 2:15, closes tomorrow at 2:15. So we're going to continue on with this nucleophilic acyl substitution. Basically, we're taking, we had discussed starting with the acid chlorides because that's the best leaving group. So we're taking those and then substituting for some weak nucleophile so that we end up with another oxidation state 3 functional group. So here's our table of those nucleophiles. And really, the acid chloride's the most common starting material to do this type of substitution. Again, that relates back to the pK of the leaving group. So we'll run through some of these. We won't go through all of them, but you'll get the general feel of what they are through the spectroscopic signatures and whatnot. So generally, in the textbooks, these are called carboxylic acid derivatives. And so what I've just made is a table that shows you the different functional groups, the nomenclature, etc. So in the first column, we have the oxidation state 3 functional group, what it looks like when it's drawn, the sort of the important part of it. The R1 or R is just the rest of the molecule. The nomenclature, and again, this is typically from finding the longest carbon chain and then changing the parent. So acid chlorides have this OYL space chloride ending. Esters are typically 2 words. The first part of it is sort of derived from the alcohol that makes up the nucleophile that did the substitution. And then it ends in OATE. Nitrile, you're just taking the longest carbon chain and shoving the word nitrile at the end. Anhydrides are basically OIC ending, then the word anhydride. Amides, you drop the E from the chain, replace it with amide. And then these metal carboxylates, again, those are the conjugate bases of carboxylic acids. And then whatever the metal is, typically lithium, sodium, potassium, sometimes magnesium. And then the rest of it is named as sort of the ester is. So of these specific examples, I've listed the molecular weights, melting points, boiling points. And you can kind of get a flavor of how that functionality affects really the boiling point more. And again, all that gets back to hydrogen bond donating, accepting abilities. So we've seen already how to make the acid chloride from the acid. So one of those was with thionyl chloride. And the reason we were doing that was the highlighter here. The OH was a bad leaving group, so we're substituting it for a good leaving group, and then now we're going to do the transformation that we ultimately want. So when the nucleophile is a carboxylic acid, and I think that reagent's wrong. It doesn't have enough carbons. It should be should be 3 carbons. So we have a carboxylic acid in the presence of a base. All that's doing is forming the carboxylate. so that we can substitute the chlorine and end up with the anhydride. So an anhydride is basically an oxygen that has two carbonyl groups attached to it. Another way to think about it is you're just taking two equivalents of an acid, condensing them together, and a byproduct is water. So that's why the product is called an anhydride. So for the most part, if you look at this, it's a symmetric molecule. So there's a mirror plane down the center here. That makes these side chains equivalent. When you have anhydrides that are not symmetric, then their spectra can be a little bit more complicated because your carbon and hydrogen sets are going to be different. The main spectral signature for an anhydride really is the IR. Because of those two carbonyls, that's going to show a unique signature. And the reason it does that is, remember, IR is based on bond stretching. So you have two carbonyls. You can have one kind of moving in one direction and the other in the opposite direction, so it gives you like this doublet looking pattern. The mass spec and proton are both yellow, so it's not really diagnostic. The carbon I colored green because you'll see those sp2 hybridized carbonyl carbons, but really IR is the best. And as we see in this region here, region 3, there's that doublet looking structure. So you have your normal looking carbonyl. It doesn't go all the way back up, comes back down, and so you kind of get sort of two in one there. And because you have two carbonyls, they can operate in different modes. That's why it sort of splits apart like that. That's almost always indicative of an anhydride. And so the other thing I want to point out is related to that formula there. So you have to have 2 degrees of unsaturation plus 3 oxygens. And so then you can, when you start seeing those type of things, then you can write that fragment down. We already saw one way to make esters. That used the carboxylic acid with an alcohol and a strong acid, so that was the Fischer reaction. We can make esters, again, starting from the acid chloride. In this case, this solvent is the nucleophile as well, and we're in the presence of a base, so sodium carbonate. And that is present to neutralize HCl. So there's chlorine, there's H. Those are the things that go away when the starting materials are coupled and they have to be neutralized. So typically, these type of reactions you would only really run when your alcohol part of the molecule is cheap. And what I mean by that is because you're using it as the solvent as well. So you don't want to have a really expensive alcohol because only one of those is going into the molecule. The rest of it you have to get rid of because it's solvent. So with the ester, now you have 2 oxygens, a degree of unsaturation, an sp2 hybridized carbon. But these are a little bit more challenging to figure out because the carbonyl and an ester and a ketone are kind of in the same range and nothing really distinguishes them. Based on molecular formula, though, the ester has to have 2 oxygens. Ketone will only have 1. So when we look at this product structure, remember I said in the nomenclature the alcohol part is named first. So this alcohol part, there's 2 carbons, so that comes from ethanol. So it would be ethyl, and then the rest of the molecule that includes the carbonyl is named. So for ethyl, 3-methylbutanoate, which of the following correctly assigns the chemical shifts to the CH2 group here and the CH2 group there? So the answer is A. Remember, when we're talking about chemical shift, if we kind of start at 0, we're then moving to the left based on what's bonded to the carbon. So since this has a heteroatom, the oxygen's going to push that signal further away from 0 than what we see in the other situation here. So that puts it at about 4. This one's at about 2. So notice it's not as much. It has a carbonyl carbon, which is going to affect it, and then this other sp3 hybridized carbon. So again, when you're interpreting spectra, if you look at the regions, you can kind of get an idea of what is affecting the hydrogen shift based on what is bonded to the carbon. So remember, we need 1 degree of unsaturation plus 2 oxygens. IR will definitely tell you if there's a carbonyl. But again, the hard part about differentiating an ester from a ketone is that those carbonyls are sort of in the same region. There's nothing about their shape that differentiates them quite a bit. So really you have to look at other things. If you're given a molecular formula, again, it has to have 2 oxygens. The proton NMR can help as well because that alpha carbon is typically between 2 to 3 ppm, the hydrogens on the alpha carbon. I mean, the hydrogens on the carbon bonded to the alcohol oxygen, again, they'll be in that 4 to 5 region. So when you're looking at spectra, you have to consider all the data you're given and see, can I eliminate one of these because a diagnostic signature is not there, and then what am I left with? What's the ambiguity? How can I increase the confidence of the structure? This is propyl acetate. So again, in terms of the nomenclature, some of these smaller molecular weight esters will use common names. So acetate is a 2-carbon unit. So that part is the acetate, and then we have the 3-carbon alcohol, so propyl acetate. Really the defining feature is the carbonyl. And so that will move around between 17 and 1800, based on, is the ester acyclic or is it constrained in a ring as a lactone? Any questions? So the next nucleophile is ammonia. An acid chloride plus ammonia makes a primary amide. So amides are classified like amines, where you're looking at the number of carbon substituents. So a primary amide will always be bonded to a carbonyl and then have H2. So ammonia itself is a gas, so typically it has to be condensed, and so the reaction has to be run at least negative 33 degrees centigrade. So that will bubble the ammonia gas into the solvent, and it allows the substitution to happen. The other thing that will form here, you see there's a NH3, you end up with NH2, and we have that chlorine to get rid of. So that'll form ammonium chloride as well, which may or may not be a problem to get rid of once the reaction's complete. So since ammonia is a gas, that can be hard to work with. There's a cryogen. An alternative to using ammonia is ammonium hydroxide. So that's just a solution where ammonia has been bubbled into water, and that's a source of NH3 that's a little bit easier to handle, and it'll accomplish the same transformation. So the diagnostic IR signature for amides is that carbonyl is in general going to be less than 1700 now. So when you're on the exam and you're looking at these spectra, you have to, they're not the best quality IR, so look at the x-axis, find the 1700, see where the carbonyl is lying. The reason it occurs at the lower wave number was due to that resonance, where the nitrogen lone pair is delocalized onto oxygen. So that carbonyl has less double bond character. So now it's moving it below the 1700. With amides in general, you still have a degree of unsaturation due to the carbonyl, but now you need at least one oxygen, one nitrogen to claim that there's an amide in the molecule. If the mass spec is odd, again, that means you have an odd number of nitrogens. So with your amide functional group, just assuming that's the major thing, you have one nitrogen. So the parent mass is going to be an odd number. The C13, you're still going to see that carbonyl C in that region, but these other things can help you, boost your confidence in claiming that there's an amide. So I said there was different classes of amides: primary, secondary, and tertiary. Primary and secondary both have NH bonds. Tertiaries do not, because now the nitrogen's bonded to 3 carbons. So with primary and secondary, you're likely to see an NH stretch in that region where you normally see, like OHs from acids or alcohols. And these will typically look different than an alcohol and a carboxylic acid. So for a primary amide, we have the 3-carbon amide, so propanamide. And as I said, even I can't read this. The 1700 line is right here. So that's the 1700 line. You can see that the carbonyl is just right below that. So that's an indicator that, okay, it's the amide. With the particular one shown on the screen here, see the NH2? Over in this region, now you see this broad stretch. It has that doublet looking thing to it. So if you can visualize what an alcohol looks like, what a carboxylic acid looks like, this is different. The reason that this one occurs is that doublet. In this resonance form, these H's, while they're bonded to the same nitrogen, they're in different electronic environments now. That H is closer to this O minus. This H is closer to that group. So they're reasonably differentiated, and that's why you see that kind of doublet thing. So this would be a secondary amide. Notice it only has one H. The carbonyl is still going to fall below 1700, but this region is not going to look like this anymore. It's going to be less intense. And then if you have a tertiary amide, the nitrogen no longer has hydrogen, so you're not going to see anything here at all. So once you identify that it's below 1700, you can go over here and maybe determine if it's primary, secondary, or tertiary. Since the intensity of this signal relies a lot on hydrogen bond donating, accepting, it's not always the case that you're going to see this pattern exactly. So lysergic acid diethylamide. I should write that in here. So this is the diethylamide, otherwise known as LSD, is made from lysergic acid. This is a naturally occurring compound. So it has nitrogen, so it's an alkaloid. The synthetic substance has substituted the acid for this diamide. So which sequence of reactions do you think will do that conversion? It's not A because this is a reducing agent. Notice the oxidation state. That's staying the same. So what we're doing is a substitution of that group now for this group. So with the oxidation state remaining the same, we have to transform the carboxylic acid into the acid chloride. So that's the thionyl chloride. And then in the second step, we're using the diethylamine. And so I guess this was more popular in the 60s and 70s, kind of on the art scene. It's a hallucinogen. And so that's kind of interesting to think about in terms of the biochemistry. I've personally never partaken in LSD, but I know people that have, and they've described some pretty weird experiences from it in terms of things changing color, inanimate objects talking to them and whatnot. So this molecule is doing something to like neurons and perceptions to alter reality. And that's interesting because it's, you're going from an OH group to just, this small change overall. None of that is really changing. So through the functional group transformation, it affects the biological properties quite a bit. So if you wanted to make the secondary or tertiary amides, you would just use, either a primary or a secondary amine. And so we're not going to go through those, but rather we're going to look at a reaction of the primary amide and again, this part of the molecule, which I'll highlight in blue here, that can be really anything. As long as you have a primary amide, you can treat it with POCl3, and that's called phosphorus oxychloride. And what it will do is a dehydration. If you look at what we're starting with and what we're ending with, so we're losing an O and H2. So again, that's water. So POCl3 is a dehydrating agent. It removes the elements of water from that primary amide to make the nitrile. And the carbon is maintaining its oxidation state of 3. So those are functionally equivalent. The other thing I want to point out that carbon hybridization changes. So you have your sort of normal sp2 hybridized carbon. You're going to observe that from 170 to 220 in the carbon NMR. When it goes to sp, that's going to shift it quite a bit. So these are between, I think, like 80 and 110 or so. And the sp hybridized carbons, again, are pretty unique in that sense, because in terms of the functional groups, they're rare. So when you see something there, you're on the track that it's sort of a triple bond. Let me see. So I have this question here, how does this happen? I won't go through the whole mechanism, but what I want to point out to you is that resonance form of the amide, it'll become increasingly more important as we move towards biomolecules. And then if you go into biochemistry, the chemistry of the amide bond, which makes up peptides, proteins, enzymes, is very stable. And the resonance form is really what kicks off this reaction happening. Because mechanistically, you have to get rid of H2 and then O with that reagent. So how do we get an oxygen out of a carbonyl? So let's draw the resonance form. And what this is telling us in terms of pushing arrows, the oxygen's nucleophilic. So see, it's negatively charged now. It has an excess of lone pairs. The phosphorus atom is electrophilic. So it has these 4 heteroatoms. 1 is oxygen, 3 are chlorine. They're all delta minus, so that's going to be delta plus. That oxygen will attack that phosphorus. And so anytime we see, a double bond, for attacking an atom of it, let's break the pi bond. So phosphorus has 1, 2, 3, 4, 5 bonds to it. And again, the reason it can do that, we're now below nitrogen in this period 3. So it has access to d orbitals. And that's important when we start thinking about DNA, the phosphorus linker between the carbohydrate units, the stability of that functional group of phosphorus, so it can accommodate an expanded octet, whereas nitrogen can't. So you don't see a nitrogen atom in the sort of strand of the DNA that's linking the sugars. So I'll push one more arrow, and then the rest of it I'll let you figure out. So that can collapse to do an elimination. And so we have these chlorines. So we'll have one of them leave. We have C double bond N, so an aminium balanced out by a chloride. And really this is the important thing right here, this oxygen phosphorus bond. So that's a really strong bond. That's why nature uses it in DNA. And that's going to allow the mechanism to proceed to get that oxygen out of the molecule. So what needs to be done pushing further arrows is get rid of these H's and break that CO sigma bond. And you can, push arrows a couple different ways to accomplish that. But overall, that's one of the more classical ways of doing this. POCl3 is not very fun to work with, I'll say that. One of the reasons is, if you know anything about nerve agents typically have a phosphorus in them, and again, that's because they're biologically active. So this reaction, or this reagent, any sort of water that's around, it will react with water as well. So you open the bottle, it'll kind of fume a little bit, and then you start smelling something and you know it's not good because it's reacting with like the moisture that's on your skin, in your nose, that sort of thing. But it'll do the job, it'll dehydrate to the nitrile. Nitriles have a couple diagnostic signatures to them. So we're talking about a carbon-nitrogen triple bond. So the IR is typically going to show that really sharp signal. It may not be very intense, but it'll be sharp. There's one nitrogen, so the mass of the parent should be odd. And then in the C13, because we have an sp hybridized carbon, those typically occur in that range. Here I have 110 to 130. These, I was talking to a student last week. These are not like running into a wall type boundaries where if you're at 131, you're ruling it out completely. It's a fuzzy sort of area when you're in these boundaries. So that's why you have to look at all of the data combined to see if things work together or they don't. So here's region 2. That was from, where's the line here? So 24 to about 2200. That's our region 2. Those are the triple bonds. And you can see it's really sharp, right? At the width, if you've taken maybe they talked about this in Gen Chem, the width at half max of a signal. So from the baseline to the top, like halfway, it doesn't span a lot of wave numbers. And so the result of that is it's pretty sharp. It goes down and then back up. And it does look different from the shape of a carbonyl. The region it is in is telling you it's a triple bond. What I mean by intensity, see how it's not going all the way down to the x-axis? These typically maybe go 3/4 of the way or maybe just halfway. So they don't have a lot of intensity in that regard. So why is all of this useful? Why don't you take a look at this slide, see if you've seen any of it before or any of the names sound familiar to you. The structure to the top left is commonly known as serotonin. So the name above it is more like the formal IUPAC name. But it has these other synonyms as well, or aliases. So serotonin. Does anyone know what that does in the body? What were you going to say? Huh? Makes you happy. So it's like a neurotransmitter. So typically, I would say to an assumption, you more think of it as like in your brain, but it's also in your gut as well. If you've heard of this, like, gut-brain axis or connection. There's this research that says like diseases can develop based on like the things you eat, because the transportation of these neurotransmitters gets affected by things. But so it's I would say like a mood regulating neurotransmitter. If you look at serotonin to now this thing, N-acetylserotonin. We've taken a primary amine and we've made a secondary amide. And in the body, that happens with this thing that's labeled in blue here. This rainbow stuff is an enzyme. So that's the name of this enzyme. It says N-acetyltransferase. So the part I'm highlighting in red, this enzyme is basically just a big acid chloride. So from the primary amine to the secondary amide, in the lab you would use that. Your body uses this enzyme, which is supplying those two carbons to make the amide. So if you do go into biochemistry or cellular and molecular biology, the enzyme names typically tell what they're doing. So if you understand, these vocabulary terms, so N-acetyl, so acetyl is the 2-carbon unit transfer, and then most enzymes end with ASE, so that's the mechanism of action. As we march towards the end of this semester, when we get into biomolecules, we'll talk about what sort of these things mean. All it is really just a large organic molecule composed of amino acids. So in a sense, it's a biopolymer that's made of individual amino acid monomers. You see this squiggle, there's these shapes that arise due to the non-covalent interactions, so hydrogen bonding. So that would be a helix. Then you have this arrow that's a ribbon. And so the sequence of the amino acids gives rise to secondary or tertiary structures based on how those secondary interactions, like hydrogen bonding, are sort of optimized. So in the next step, the N-acetyl serotonin, so now look at this enzyme name. It says O-methyltransferase. The phenolic hydroxyl group has now been turned into a methyl ether, so O-methyl. So what is this enzyme equivalent to in the lab? This would be like methyl bromide. So it's supplying one methyl group and there's a leaving group. And over the course of time and history, these enzymes have evolved to do very specific things. So it says N-acetyl serotonin O-methyltransferase, meaning it's not going to methylate any Joe Schmo alcohol in the molecule. It's going specifically after that type. And so what I've shown is just two enzymes. So there's a lot of different enzymes in living organisms that carry out very specific functions. And so what does melatonin do? Makes you sleepy. And so why should you not stare at your phone in bed? The blue light is, killing your melatonin supply. So on these like iPhone or Android things, how they have this like warmer, cooler colors at night, or you can set that. It's basically to, help you not doom scroll till 3 a.m. And so it kills the blue light, which in turn doesn't affect your melatonin as much. And allows you to be a healthy human being. Have you ever worn like orange glasses? It's pretty wild, right? The difference, like when you put orange glasses on, like I have a pair in lab, like orange safety glasses. It brings down the stress a little bit, doesn't it? With these fluorescent lights, there's so much like noise pollution. Like even though you're looking through an orange kind of filter, things get a lot clearer and the colors are a bit sharper. So if you do have like stress issues, try wearing like orange glasses. People may think you're weird or like you're trying to impersonate Elvis from the 70s or something. But it does, I think, reduce like light stress that you might feel. And again, the point of showing you this is that the organic reactions you learn, if you go on further into the biology part of it, the enzymes are really just mimicking these reagents that you see here. So the fundamental mechanisms are kind of the same. A little stuff might change with shuffling protons around for acid-base chemistry. Any questions? So let's kind of put some stuff together and look at this transformation and see what sequence will achieve this. Let me put a dot right here to say that that carbon is that carbon. And all of this other stuff in blue, there's no action happening there. So we're starting off with a carboxylic acid, and we're ending up with an acetal. So oxidation state 3 to 2. And then the other thing is we've added 2 carbons. So D is the correct choice. Overall, we need to reduce that carbon with the red dot because the oxidation state's changing. And we have to add 2 carbons to it. So the best way to do that, first we're going to treat in step 1 with lithium aluminum hydride. That's going to reduce it all the way down to the primary alcohol. So that's the product of step 1. Now we're going to oxidize it back to the aldehyde. So that's the Swern oxidation. And so the numbers in blue are oxidation state. So now that we have a carbonyl, we can use the Grignard reagent in step 3. So ethyl magnesium bromide, that supplies the 2 carbon atoms. So we have the, sorry, that should be 1. We have the 2 carbon atoms in there, but now we've reduced the oxidation state. So step 4 brings it back up. So a secondary alcohol now becomes the ketone. So we're at the correct oxidation state of 2, but we need to take the carbonyl to an acetal, and that's the last step 5. So the carbonyl with an alcohol under acidic conditions keeps the oxidation state the same, but then changes the hybridization of that from sp2 to sp3. So the other probably best distractor answer is C. It mimics sort of the same stuff, but the Grignard doesn't have enough carbons. And then the step 5, the alcohol part, has too many carbons. The issue with choice B, you're starting with the Grignard, but the starting material is an acid. So that's just going to do an acid base and not proceed any further than step 1. Choice A, step 1 is what kills it here because sodium borohydride will not reduce an acid. Everything after that looks fine, but we can't get past step 1. So the last couple slides here deal with reduction. And so we're going to return to lithium aluminum hydride as a reducing agent when applied to amides. And there's an important distinction about LAH with these oxidation state 3 functional groups. So we learned prior that lithium aluminum hydride was the strongest reducing agent. It acts on OS3 and OS2. So for example, an ester will be reduced to a primary alcohol. Now look at to the right-hand part of the slide here. We have this same acyl group, which I'll highlight in blue. So that part's the same. But it's a primary amide. A primary amide treated with LAH does not give an alcohol. So let me run through sort of the intermediates over here so that we can understand why this is different. So I'm just going to say LAH is, so H minus in terms of reactivity. So it's going to attack that carbon and will form this intermediate. So that's going to collapse, and then that group will leave. And so now we have an aldehyde. That's going to get further reduced. So another equivalent of hydride. And at that point, it's just an addition. There's no further elimination. So you've reduced it all the way down to the alcohol. The key difference is this thing right here. See that O-ethyl group, how it leaves? This will not collapse and have NH2 minus leave. Because as we saw before with leaving groups, NH2 minus is a really bad leaving group because we looked at the conjugate acid of that and the pK was about 40. So the take-home message here is when you're reducing an amide with LAH, that group is retained, and the carbon itself is just reduced. So again, in the ester, that group is gone, right? The O-ethyl, you don't see it anywhere in the product. So no matter what ester you start with, you're always going to end up with a primary alcohol. The utility of an amide, whatever this class is, you're then going to end up with that class of amine. So if you start with a primary amide, you end up with a primary amine. And so why is this useful? Well, we saw we can make amides from amines and acid chlorides. So it's another way to access these classes based on the substituents of the carbons. So I want to just generalize. When I say NH2, you can think of that as the H as being carbon substituents as well. It doesn't have to be NH2 specifically. And so that will translate into these other amides. So really, you can't do substitutions or addition eliminations with amides due to that pKa argument. So let me first go through the amide classification, and I'll circle back to the stuff on the top of the slide here. So we classify these the same as amines. You're looking at the nitrogen and how many carbon bonds it has. So with the primary, you just have that one to the carbonyl. The secondary, you have the requirement to the carbonyl one, then you have a second carbon bond. And then the tertiary, it's all carbon substituents, and then notice there's no more NH bonds. So you're not going to see anything in region 1 of the IR for those. So these are the classes of amides. And so why is this nice now? Because we can reduce these, essentially removing that carbonyl to get amines. This complements these other ways we've learned of using these protected nitrogen reagents to get nitrogen in the molecule through SN2. We also saw reductive amination to make secondary or tertiary amines. And now we have this other strategy that will allow us to make pretty much anything. So this molecule is N-benzyl ethanamine. It's a secondary amine. We're going to use an acid chloride to acylate the amine. And now we've ended up with a tertiary amide. So from the new NAS mechanism, that chlorine has been substituted for the rest of that amine. So just to recap, one way that we could make, how could we make that? We could take a primary amine plus an aldehyde, do a reductive amination to get that. That's one way. Or we could split it the other way, where this has the carbonyl and then that's the amine. But that allows us to get to a secondary. We can then acylate it, and then the LAH will reduce that oxidation state. So what would be the product of that reaction? So C. Again, the key difference with this, so LAH with an amide, there's no leaving group. All the carbons are intact. The only thing that is changing, so that oxidation state 3 is just being reduced to 1. So from that amine, again, we can make that 3 different ways with reductive amination. We can now make it 3 different ways with this strategy, acylation, then reduction. So that is the last slide for this. Do you have any questions before we wrap up? And you have your exam in a couple minutes here. Yeah.
Is zip grade still working with the, like everything else being down?
What's down?
Canvas is down, like all the other major stuff.
Everything that's associated with the Amazon software is down.
I did not know that. I don't know if ZipGrade is hosted on Amazon stuff or not.
It is. It uses AWS to use its hosting. It's not its hosting, but it's data hosting. So if you upload stuff to it during the outage, it's not going to go through all the way.
Well, I don't have my laptop here. I only have my iPad. If someone starts it at 2:15 and you can't log in or something, just send me an email. If there's like issues getting into ZipGrade, you don't have to go through Canvas to get to ZipGrade. You can just go to ZipGrade. If you can't get into that, just let me know. And then I'll readjust the times. If it's whatever the start time is, you'll still get 24 hours. You know what I'm saying? If it doesn't open exactly at 2:15, you'll get 24 hours when it does open. But you'll have to let me know because I won't be able to check it on my iPad.